OK，嗯，yeah, from our last class, we learned lots of scheduling algorithm for CPUs, CPU scheduling. But in the modern operating system, we always mix of different strategies, CPU scheduling strategies together to achieve a very complicated purpose, like this multi-level queue scheduling. Ready queue is partitioned into various separate queues, not only one queue, multiple queues. Processor write uh, each queue has its own scheduling algorithm. So this is for different priorities. Different priorities. Each queue has its own scheduling algorithm. So the disadvantage is uh, so it's inflexible because some processes are permanently assigned to a given queue. So this is a multi-level queue scheduling. It's not flexible. So other ways is a multi-level feedback queue scheduling. A process can move between the various queues. So still the it's a queue and the multiple queues it can process can move between multiple queues. You see, this is a very fundamental method scheduling algorithm that is uh, for different combined with other strategies like this one. Multi-level queues, priority based on process types. So real-time processes, this have a real time. Real time is a highest priority. It must be response quickly. Otherwise, you feel this latency, like our screen. So once the screen has some latency, you feel, oh, the screen, the UI is freeze. So this has the highest priority. This one has the system process. Important. And some others, other than the batch process, some are not important, has lowest priority, like a file read and file write. File reading and file writing is very slow. And if delay for several milliseconds, it's still acceptable. It's not very emergent. So it's the lowest priority. So the queue, the priority, the process queue has different priorities, and each priority has a queue. So and maybe the process can jump between them. Okay. It's more complicated. In modern system, it's more complicated. Okay, this is the scheduling in OpenMP. OpenMP, do you remember we discussed OpenMP? It's implicit for implicit threads. So when I have this line, paradigm OMP parallel. So it's run in parallel for multiple of threads, right? Multiple threads. So before we only discussed this parallel for multiple threads. How can they split the task? Actually, it has a scheduling strategies like a static. Static is divided before running in compile time. Divide the chunk in compile time. So I from 0 to n. 0 to n is the size of an array, right? The split the array statically. Dynamic means the split during the running time. Guided is like dynamic, but chunk size shrink over times. Guided. So each time is smaller and smaller. The chunk size is smaller. Also is compiler running decided. I never use this. I always use the static or dynamic. Static or dynamic. Okay. Uh, oh yeah. Oh, this I can show you some code. I like to show some code. Uh, mm, Oh, can you see here? It's a pthread scheduling. Now you are familiar with what is pthread. It's to create thread in a process, right? This is a source code from the textbook. Source code from textbook. You see, here is we create how many threads we create? How many threads we create? Create threads. Yes. See here. Create threads. It's from 0 to number of threads. We create this size of threads. It's okay. We use the pthread create this size of thread. Yeah, good. But all this thread, which strategy you want to use for scheduling? Actually, in Linux, we can set that. We can set that for which thread? Which? Yeah, here. See here, pthread attribute. You can set the scheduling policy. Scheduling policy. It's this is attribute structure. This is setting to schedule other, and the other one is you can also set it to FIFO. Most simple one. So we already discussed, but FIFO. You also can set to RT. What is RT? Rounded robin. RT. I guess it's a rounded robin. That's that one, and the others. Here I have the very detailed. Yeah. Oh, I guess this is the error. Should be schedule FIFO and schedule RR. So that's the error. Okay, this one. Rounded robin. Should be rounded robin. We already know this too. What is rounded robin? Do you remember? Forgot? Yeah.
You spend a little bit of time on each one and you keep going in a circle and you go back till they're all finished.
Good. Why? So this is better than FIFO in which case? Okay. Real time. Round robin, because the split for different for time slice, it's can have a quick response. Think about one process has a long time running, and rounded robin can give a quick response, low latency. Okay, so now when you finish this course, you know how can you select this one. Okay. Sometimes if you want a quick response, you can set the rounded robin here. Okay. Next example is OpenMP scheduling. We say here is OpenMP is check n is size of 20, very small, and here is set to the setting 4. That means split the trunk from 0 to n 4. 4 is unit as a 4, and they can run in parallel. I don't need to tell the OpenMP how many cores I have. It can create 8 thread because my Mac has 8 threads. This is dynamic trunk size. This is the schedule in running time. This is guided. This is auto. So when it runs, you see, thread 1 handle A4. Where is thread 1 again? Because thread 1 is because it's printed in because of 4 threads running at the same time. So printed out don't have some fixed sequence. It's totally arbitrary, not random, arbitrary. Third one handle A4, third one handle A5, third one have A6, 7. From 4, 5, 6, 7, third one. It's third one. Trunk is because the trunk is 4. And thread 2 handle 8, 9, 10, 11. Okay, this is about static. It's already assigned. But for dynamic, this may be different. Okay, thread 6 handle a bunch of them, handle lots of them. But thread 3 only handle this one. It's because it's split half dynamically. Dynamic means we want to make this work totally averagely separated to split to the threads. Dynamic is automatically assigned. Dynamic don't want someone doing the work so heavy, someone doing the work so late, so light, averagely. Everyone has the same work. This is to achieve good parallel. Right? This is dynamic. Good? And you hear it's good? Let's go. Let's go on to the next topic for CPU scheduling. Oh, more readings. Because all we discuss now for scheduling algorithms is all based on rules. We have lots of rules. First in, first out, rounded robin. It's all based on rules. And our current research the machine learning, some AI is very popular today. There's lots of research on machine learning. There is a supervised machine learning. Predict the job duration. As we can see, we cannot predict the future. We cannot predict the future, but we can approximately sum of the job. Not accurate, but approximately you use the machine learning method. This is use the reinforcement learning. Learning scheduling decided where reverse. It gives the reverse. Reverse what? Reverse is can we averagely split the work? Is that possible? All the threads finish the work at the same time. So yeah, the reinforcement learning, the graph neural networks. But all of this have the limitations. All this is very heavy. It's a rule-based. First thing first out is simple, light, and don't need some data to learning. So don't need training data. All this need training data. This is so heavy. So why they still use this? Because in some scenario, like a server, like cloud computing, the work is very heavy. Like one process can run in one virtual machine, right? It's very heavy, very heavy. So this is useful. You know, scheduling algorithm it's possible to use some AI, but this is very heavy method. If you're interested, you can read those papers and pick someone to do the project. Do you know? We have the project for like 10 bonus marks add to a total. So if you're interested, find someone talk with me and because this one all this paper is very new, all very new and recently very hot research area. Okay. Good. Now we can go into our next chapter. Synchronizations. Okay, synchronization. Because CPU scheduling the process, but scheduling the process in the CPU level. All this is application levels. So it's a scheduling algorithm is like the first thing first is running on the kernel mode. It's a CPU level. It must running on kernel mode. We cannot control that. Okay, we just say some we can say some threads. We can select which scheduling algorithm we can use. Right? But actually, we cannot control the CPU, how the CPU gets scheduling. But this is totally running on the user mode. This is always used to some of the application. We want to get the resource. Who will get the first? Who will get the second? Okay. This is the high-level programming technique. When I was the interview, they always ask you the concurrent questions, like the synchronizations, concurrent programming, like this. It's very important and classic in this course, like mutex locks. We use locks, semaphores. semaphores. The locks and the semaphores are widely used in Python and C. Python and C also for this. The monitors is Java provided. Java provided. It's widely used in Java. And then other I try to cover the other synchronous method because it's very hot, like the atomic instructions, the CPU levels. CPU, we use the CPU instructions to do lock and lock free. It's a hot research area, and especially this ones, the Golang. Anyone knows Golang? Yeah? No? Okay, later we'll discuss this. It's widely used in industry. So background. Let's look at the background. Processing the thread can exist concurrently. Concurrent, what's the concurrently means? Concurrently. I suppose you not forgot what is the concurrent. Same time. Each process may have multiple threads. So multiple threads can run in concurrently. Concurrent. What's the difference between concurrent and parallel? Concurrent and parallel. Yeah, maybe you forgot that, right? So parallel means physically parallel. I have 8 cores in my laptop. So 8 processes or 8 threads can run same time. But concurrency means not be physically parallel. If I have 8 core, but I have thousands of threads, it still can run. Looks like parallel, but actually not. Actually not. So the CPU, we know CPU scheduling. CPU will do context switch. They do thread 1. Oh, thread 2 coming. Thread 2 has higher priority. So doing context switch to thread 2. That is or they can use some scheduling algorithm, scheduling like a semaphore, like a semaphore, like a monitor. They can switch to the thread 2. To switch to thread 2. This is concurrency. The concurrency not means they are physically doing parallel. That looks like parallel. Okay, looks like parallel. They are needed some. When you say the concurrency, they need synchronizations. They need synchronizations. So yes, concurrent access to shared data may result in data inconsistency. 2 threads access the same data. So which one is first, which one second? Maybe not consistent. Maintain data consistency require mechanism to ensure all the execution of a collaborating process. Let's see some examples. Let's see examples. Okay, producer and consumer problems. This is very classical ones. Here, a producer produces information. This is buffer, right? A producer produces information and put into the buffer. The consumer consumes the information, take it out from the buffer. So the producer and the consumer must be synchronized. So that synchronized for what? Okay. I discuss producer, you discuss the consumer. I can try. The producer information put into the buffer. Okay. The producer finds that, oh, it's empty, I can put. And when this buffer is full, the producer should stop. It's full. We cannot over the buffer. The full. This is the one synchronization for producer. How about the consumer? How about the consumer? This is the buffer is shared data. Say the producer and the consumer shared data. How about the consumer? Yeah.
If the buffer is empty, then the consumer has to wait.
Yes, good. If the buffer is empty, consumer must wait. If the buffer is full, the producer must wait. And both the producer and the consumer cannot access the buffer at the same time. Otherwise, the producer put data here. The consumer say It's in there or not in there. It's inconsistent. It must be producer put data here. After that, consumer can take the data. So the buffer, only one user can access the buffer at the same time. So the buffer should be locked, right? Three things: producer, consumer, and the buffer. Three things that need to synchronization. Okay. So that's a good example. We discuss this example later. Before that, we must have some background. So a solution to this consumer producer problem can be made by integer counter, right? Integer counter to keep tracking the number of full buffers. So this counter to show that so this counter to show that which buffer I put the data in. So initially the counter is zero, and the counter is increased by counter. We know that this is in C, right? Increased by 1. By the producer after it's put new buffer information, and the decrease by 1 is by consumer take the data from a buffer. It's increased by 1, decreased by 1. It's good. Until here is good. So we can implement this by increase by 1, by decrease by 1. But in your mind, you'll see the increase by 1, decrease by 1 is not atomic instructions. That means in the CPU, it's split into 3 instructions. You see, CPU has registers. CPU load this counter into register, and in the register it's increased by 1, and then write the register value into the counter. Counter is in the memory. Right? So this counter increased by 1, it can split to 3 instructions. Okay, 3 instructions. This is also 3 instructions. So when it's running, so they can interleave with each other. Who will be the first and who will be the second? Producer and the consumer. We never know that. It's not random. It's arbitrary. Maybe sometimes it can give you the good result, correct result, maybe sometimes not. We cannot rely on that. How about this one? Is that correct? Is this correct? So counter increased by 1, and counter decreased by 1. This they interleave with each other. Initially, counter is 5. Increased by 1 and then decreased by 1. The result should be, is this correct? They interleave with each other. See? Think about this. What's correct? Yeah, try. Try to try.
2 different counters.
Yes, it's a counter. No, 1 counter. So the counter is the same same value in the memory. The counter is in the memory. Registers are different. Registers are different. The CPU must load this memory is counter to the registers. It may be loaded to different registers. But can you follow up this question? Yeah. No, what? Well, why not? It's the well, both different registers. So yes, initially it's 5, but the result is 4. It's not correct. Why is not correct? Has anyone seen that? Because it's a counter in shared value. This is a counter shared value in the memory. This counter, register 2 read the counter here. This value is still not yet written by the CPU from register. So this is dirty value. This is dirty. This is register increased by 1, and the register this should be written into the memory counter, but not yet register 2 read the value from a counter. Here, the counter here is dirty values. Dirty means it's not correct. It's not correct. Here, not correct. Say here, counter register 1 read the value from the register 1 read the value from a counter, and register 1 increased by 1, and then it should write it into the counter. But now here, register 2 read the value from a counter. This is the dirty value, not correct. This is the problem. Okay. So in this case, it's not correct. But in other case, if S4 running before S2 here, it's correct. But how can we control that? Cannot control. Okay.
Can we not lock the counter?
That's why we need lock. Okay, good. Because I can show you a code. I prepare a very easy to understand code for this. Okay. Here is I implement this condition. I implement the n is 100 million. N is 100 million. This means we're doing 100 million times adding plus 1. This is increment risk. This one has risk condition because counter equals counter plus 1. It's not a log, not atomic, I just put it here. So this will split to 3 instructions. It can interleave with each other. And the next version is I use T-thread lock that. So one thread can access it at the same time. So it's safe. Lock it means safe. We're not yet discuss lock, right? And this one is atomic. We use atomic instructions, fetch add, atomic fetch add. This will call atomic instruction. So this means this will not split to 3 instructions. This is the 1 instruction. This is more information, but this is not easy to use. The atomic fetch add instructions. So let's say we have 3 threads. 3 threads, right? Create create 3 threads, and then we're doing the this is doing the increased risk condition, and case 2 is doing the mutex, and case 3 is doing atomic. So until here, you know the code. So my question is which one is efficient? Which one is the fastest one? Risk condition, lock, or atomic instruction?
Probably the race condition would be fastest
No, why?
because there's nothing slowing it down, no other blocks.
Sure. Yeah. How about the lock and atomic instruction?
They'll be a little bit slower because they have to do extra processes.
Lock, yes. And lock and how about the lock and atomic instruction? Which is the faster? Okay, that's what new thing. Let's say result. So the risk condition is mostly for the really fast. How many seconds is it? 1 million seconds they used. And the mutex locks is very slow. With 5 seconds, they need to do the 5 seconds. I'm doing the 100 million times adding operations. Mutex is very slow because lock, we need to lock the data and unlock the data. When other process say, oh, this data is locked, other process will, other thread will sleep and wait. But this atomic instruction don't have this sleep. Atomic is the fastest. This one. Atomic is fastest. Sorry, atomic is better than Newton. Risk condition is not correct. This is meaningless. It's not correct. So here I compare use optimize. So it's GC's optimization 3 is the best optimization for performance. So it's running time is here. If I don't use the optimization, you see, if I don't use the optimization, this condition, this result is much slower because I don't use the optimizations. And atomic instruction is still slower, a little slower. This is a very obvious, but slower because I don't use the compiler optimizations. I guess here, if you use the optimizations, it will use the cache to speed up the calculations. Cache here. This will be just in the compiler part.
Does the minus 0.3 also reduce something with the race conditions? Because it appears when you add it, it makes the right result, and when you take it away, the race condition comes up with the wrong result.
All give us the right result.
Yeah,
Oh, yes, this one.
yeah.
This is, I don't know. This is because the CPU compiler doing the optimization. I guess it's put into the cache and doing the calculation on separate CPU. Separate the CPU cores. And after that, they add it together. So it can give the right result. Here, they can give the right result. But don't rely on that. Maybe different CPU, maybe next time it's not correct. It all depends on how the compiler optimizes this. That's why I say it may give you the good correct result, maybe not. Log here is always give you correct result, right? Atomic. This is the log and atomic is safe. Log and atomic is safe. Good. Anyone has a question here?
Under in the 29 section, where you're talking about doing it without the optimization, there's more words there. So the race version may give correct results and do. You know, just scroll that over.
I just give this comments. Due to the cache. Remember,
Cache was possible to still give you the right result. But
yes.
Not reliable.
No, never relies on that. This is very dangerous. You maybe come across some of the bugs in the industry. This time running very good. Change another environment is wrong.
So if you run that several times, it's possible that we won't get the same answer.
I don't know. I cannot trust. We cannot trust. We don't know. We don't know. Maybe this version is the compiler give it good result. Maybe you update the version is wrong. Never use that. This is very dangerous. Never rely on that. It's all depends on how the compiler optimizes this. Good. Very interesting. Why don't you experiment? I find that. Good. So this I saw the code here. You clear. So why it not give you the correct result? Okay. So that's why I need a concept of the critical section. Critical section. It's to consider a system has a unprocessing. This is described in the textbook, right? The very academic ways. The unprocessed, like or unthread. That's a critical section. It's a segment of the code. So in this critical section, simply speaking, it's only one process or thread can access to this critical section. Critical means only one can access it. That's critical section. This critical section solves the problem of the data racing. Only one process can slow this. So each process must ask permission to enter the section, and the existing section, then remainder sections. We will use the critical section to discuss this. So this is the critical section. Every time the process enters the critical section or enter section, going to the critical section, and then exit critical section and the remainder section. Critical section means only one process or thread can enter this critical section. This will solve the data racing problem. data racing problems. Solution for this critical section, it must be has the properties of a mutual exclusion, like the locks, mutual exclusion. One thread take this lock, others cannot take. And no deadlock, no deadlock. Live lock, also live lock, no locks. And no unnecessary delay, and eventual entry. 1, 2, 3, 4. 4 things we must consider about once we use the critical section. We must consider about 4 problems, 4 questions. Question: what are the safety and liveness property of a traffic intersection? Like this one. Traffic intersections. This is very good examples. Traffic intersections. Start with mutual exclusion. It's good. Where is the critical section? Yeah. Here. Here the critical section. Right. Only one direction can go into this critical section. It's you see it's locked. It's locked, right? And otherwise it cannot come in. Otherwise, it's the collision happens. Okay, next one is deadlock, live lock. Deadlock, live lock. Do you have the deadlock? Yeah. Signal. Assume the signal is correct. If the signal is wrong, it has deadlock. Right? Deadlock. Traffic jam, deadlock. How about live lock? Okay, you may don't know what is live lock. Okay. This is deadlock. Deadlock. Say this is 4 directions, they block into each other. Nobody can move. The deadlock happens. So this direction want to go here. 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 This is totally blocked to each other. This is the blocking cycles. Blocking cycles. This is deadlock. I guess that's the traffic lights is broken. So the deadlock happens. How about this one? This is I find a good example to show the live lock. The deadlock is nobody can move. But live lock is different. Live lock is this car can move. They always going around this cycle. Cycle round and round. It cannot go up. This is live lock. Live lock means everybody can move, but make no progress. So say this can move, it cannot go up. It's live lock. Deadlock and live lock. We also lock. We all say 2 locks, deadlock and live lock. And how about the next one? It's a no necessary delay. Any delays? No. Maybe the red lights are so long time, cause some delay. That means this is necessary delay. Okay, here is a unnecessary delay. The lights is necessary delay. It's not unnecessary delay. If the lights turn green, but you don't go, this is the unnecessary delay. So no, right? We assume everybody is smart. Okay, and the eventual entry. Finally, everybody can go pass the cross. Good. So safety. So when discuss, we call it safety. Safety is how about safety liveness? Safety in this means no 2 green lights at the same time. So otherwise the collision happen. It might be safety. So this strategy. So it means no collision can happen. Safe. Liveness is the lights will eventually be green. So it means that eventually can pass the intersection. Think about a very special case. All the lights are red. It's safe. It's very safe. Nobody can move. Yes, but it's not liveness. It's dead. It's not liveness. No. All the lights are red, so nobody can pass. It's safe, but not liveness. So safety means here liveness. Okay, so every kind of synchronization problems, we always ask this deadlock, live lock, safety, liveness, this kind of questions.
Is it fair to say that safety and liveness are like basic equivalents of the same spectrum? The more safe it is, the less live?
No.
Or
No, from this intersections. We can do our traffic lights, no more use the data use traffic lights can protect the safety and the liveness together. It's not some if you want more safe, you must sacrifice the liveness, right? So you're waiting in the traffic lights. This is the necessary waiting. Necessary waiting. It's not unnecessary waiting. So you can achieve safety and liveness together at the same time. Good. Okay. So that's we solve this solution critical section solution by use logs. We already show the code of use logs, right? So the easy acquire log, going to the critical section, then release log, then reminder sections. Reminder sections means otherwise can go into otherwise tell the other body. I release the log, other ones can go into logs. That's a critical section use logs. Use logs. Okay. Mutex logs. Mutex logs. Open system design building software tool to solve this. I say the pthread already. I just saw the code. The pthread already provides the logs. It's a simplest way is a mutex log. The product is a critical section by acquire log, which is log, and release log by unlock. This acquire and release must be. We are talking about the implementation of acquire and release. It must be atomic. Remember, don't forget our race condition. Acquire and release must be atomic. So the log can be a binary number, true and false. If lock is true, unlock is false, right? So it's a integer, binary integer. Only have two values, lock or unlock. So the operation must be atomic. The implementation. Like this is implemented by the hardware atomic instructions. Like use the compare thread. Later we'll discuss this hardware atomic instructions. All implemented by context switch and scheduling to avoid busy waiting. Okay, two kinds of implementation. One is in busy waiting. The other one is use avoid busy waiting. Busy waiting means so other thread will busy checking, not stop. And use the context switch is other thread can sleep. Context switch to the CPU will switch to other threads. Switch to other threads, and the other thread just sleep. And then when the lock is when we can lock this, it can be wake up. Good. Okay, acquire solution using mutex lock. Acquire lock, the critical section, the release lock, release lock. So one is use okay, spin lock. Okay. Busy waiting means spin lock. Busy waiting consume CPU cycles without doing anything useful works. The busy waiting. They use the spin locks, like the thread will spin at local, always checking. Once the thread is unlocked, the other thread will check. It's a spin lock, because lock just spin with waiting, spin lock. Okay, later we'll show the code of spin lock. Although busy waiting with the CPU cycles, it save times, but not waiting the context switch. Context switch need a system. Context switch is slow. Need to save the current state of the thread, and the CPU will wake up another thread to run. The context switch is slow. Spin lock don't have any context switch. So this is trade-off. If the work is very tiny work. It's the work it takes time less than the contact switch, so it's meaningful, right? The spin lock, it's meaningful. It's busy checking. Its work is very heavy. It's not worth for that. Its work is very heavy, not for that. So that's why I say it's a spin lock is very useful in multiprocessor system when the waiting time is very short, shorter than contact switch. Here, the one thread spin on one process. So the best way is not like the threads, number of threads over the CPU cores. But another complete the critical section. The threads have its own cores. The threads itself don't have a contact switch. 8 core have 8 threads. Then you use a spin lock. It's good. But when you use a spin lock, it try to minimize the contact switch because the work is very tiny. Okay. Question: how about a single processor machine? Then because maybe 20 years, all the CPU is a single processor, single core. The single core can we use a spin lock? Yeah.
It'd be a big waste.
Yes, in the single core CPUs, it's impossible to do physically parallel. Physical parallel. So one thread takes the core, and the other thread come. They must do some contact switch. Here you use spin lock. It's totally waste. It's meaningless. Okay, now you know that. But currently, our CPU has 8 or 16 cores. Yes, you have 16 threads. So that is when the work is very short, it's meaningful doing spin lock, busy checking, waiting. Okay, take a break. Back 10 minutes later, come back.
What is Mutex locks exactly? What is it?
Mutex?
Yeah. Like it says, the issue is busy.
Okay, yes, here we discuss the 2 implementation for mutex.
Yeah.
So this one is busy with mutex lock.
Okay, so busy waiting, spin locks, they go together.
So no, busy spin lock is the one implementation of busy spin lock.
Okay, so busy waiting is.
Spin lock
one
is
of the problems.
later I will say spin lock is a concept in the kernel, free.
And all the other processes are waiting, because it's locked. It's taking the process. Is that what's?
No. Spin means you lock this result.
Yeah.
I can't check. I just busy checking. I always ask you. I not stop.
Oh,
I not
busy
doing
is the other process. Well,
Yes.
I'm working and you're just waiting.
waiting.
Busy.
Waiting. If waiting is a busy checking. Waiting is a busy checking. I always ask you. Are you free? If you release a lock, I think I'm not a stop. So that's why I say it must be on multiple processor. The other implementation is the contact switch. So when I come to see you, you take the source. So I will go to sleep because doing contact switch is still doing other things. So once you release lock, I do contact switch back. So I not ask you. But this spin lock is confusing. But spin lock when you release internal.
Okay. And it's used against set because if it's going to be a short time.
Short time.
Short time and bother contact switch, you can just wait to just ask maybe 2 times and then you have the process.
Yes, good. Yes, good. Can you understand it? Thank you. We have a class quiz today. Submit before 12 o'clock. Okay, you can submit on the blackboard or submit in paper to me. Both are fine. It's not so next class we can come into the class early. Okay, let's say you can have 20 minutes to finish the quiz. Make it submit before the 12 o'clock. I will submit to the assignments now. Okay. Submit to assignments. Okay. Which one? Assignments here. Oh, no. Experience. Assignments. Assignments. Okay. Quiz one. Quiz one. Oh, there's so many files. Quiz one. Oh, no, here. Quiz one. Okay, quiz one. It's unlimited. The due date is today is 2. Okay. Oh. Oh, no. Okay. 10 marks? Yes. Quiz one. Make sure you can see that. Make sure you can see that. What? Okay, this is the question. I can make it larger. Can you see that? Oh, we are not yet discussing semaphores here. We covered it in the next class. The time. Okay, thank you today. Good.
So this is do that too.
You know, it was so, it was not the other thing. I first say something that's wrong. Thank you, and your afternoon is good. You can handwriting and stuff, submit to me on the, or you can do that. To the assignment.
We can submit online to it, to the.
Yes.
It's like the quiz, we know.
You can do online, you can do on big, yeah, you feel like it, we can. You can do the second one. The third question. You can still get third one. Still have you can do later. Still do later. I try to cover this one in the next class. Okay. Let me just. The first one. You know. You can finish third question today. Oh, good. Yeah. I'm doing a little slower introduction. Not yet covered. They can do today.
So are you going to change the due date to like later?
Yes, I obviously the today. I think today to today is like 4 o'clock. Good, 4 o'clock. Good. Any questions? Good. On the first and the second one, good. Both like 10 to 4 p.m. Okay, I can do the later. So let's finish the semaphores. So now you can finish semaphores. You know how to do that quiz. So see here's here I give the code of the spin lock. Spin lock is spin lock is this one is only available in kernel. It's not available in user mode, but user mode is still possible. We must use atomic instruction implement by ourselves. In the kernel, it has a library. Library is called yes, here's this type. This type is by in the kernel. You see, it must include in the head file of a Linux kernel and spin lock. This is spin lock. This is supported by the Linux kernel. The spin lock. So here the spin lock acquire the lock, acquire the spin lock. So the counter will increase by 1, and then print k is in the kernel and print k. In the user mode, we use the printf. In the kernel, we use the print k. Print k, then the spin unlock. This is the spin lock in kernel mode. Spin lock. Spin lock means the other thread come, it will busy waiting, busy checking. It is not doing contact trace, busy checking. Here. Now, it's the whole code of that. We always want to try to run it. In our second lab, you must install this mode into the kernel that it can run. Right? After running, it must remove this mode from kernel. Insert and remove. Insert and remove. Said mode init, and the mode exist. Because this is the kernel. So spin lock is in the kernel. But we still can do in user mode. Okay? Lock with this is user mode. We implement with user cast atomic instructions. Cast atomic is the compared swap. Uses atomic instructions. Where it is? The cast lock. Cast atomic instructions is here. Atomic compare exchange weak explicit is exported by C++. I guess it's C++. We see. Oh, this is not. I don't include some Linux kernel head files. It's supported by the Linux C. This is will use the compared swap atomic instructions to log, not acquire log. If it is the expected value, it's this state will compare with the expected value. If this equal set to 1, is equal set to 1. If it's other, that means if it's unlock, we lock it, and then it will finish in atomic instructions, then return, and then it's unlock means it's also use unlock don't use some atomic the compare swap. It use store. Write. Storing means writing to the memory. It must be atomic. Don't forget to have cache. Maybe the value loaded into the cache to speed up the memory access. So the data value is not only in memory, maybe in the cache. So atomic write stop here is to ensure that it's write to the memory. Write to the memory. So it has atomic store. Atomic store here. Okay, see the code. See the code. This is spin lock. And pthread synchronization. We use pthread to implement the lock. Pthread lock, pthread unlock. You see this already see this in the source code. So pthread lock and unlock. Before that, we must init that. And after that, we must destroy that to release the memory resource. In C, you must manually manage the memory. Don't forget to destroy the lock. It's in the user mode. User mode. Okay. So this is code. This is code. Now here init with now means default. This means default mutex attributes passed. Attributes. Then you use the mutex lock and unlock. This is to avoid the busy waiting. We use the lock and unlock, avoid the busy waiting. We say the spin lock is busy waiting. Spin lock is busy waiting, always checking. But in the work here, the critical section work is really heavy. like take 1 milliseconds, much heavy than context switch. Context switch is much heavier than context switch, maybe like 2 times of a context switch. It's better than we use this lock. The lock is other thread come will sleep doing context switch and sleep. It's avoid busy waiting. Okay, good. Any questions here? Go on. Yeah.
Does that example destroy the lock at all, or does that?
Oh, destroy the lock. Destroy lock. I don't show here.
But it should at the very end somewhere.
And no. Don't forget in your code. Don't forget in your code. Here I show that's not important. It's not here. Here is a spin lock in kernel mode. Okay, I just show a spin lock. Spin lock is busy waiting. Busy waiting. I only pick up some important parts show here, and I have the full source code here. It's a busy waiting. It must be running kernel. Hey, here, it might be running kernel. It's a kernel. Okay. Okay. Now going to semaphores. I try to cover the semaphores. Then you can do in the quiz. Okay, semaphores. So lock sometimes is simple, but some things. But the semaphore is more functional synchronization tools. And it's widely supported in current programming language. It's provide more sophisticated ways than the mutex. Mutex is simple, only can use lock and unlock here. But semaphore is a integer variable. S is integer variables, and can only be accessed via 2 atomic operators. Here, atomic operator. Okay, why it must be atomic? Why it must be atomic? Yeah, because this is maybe lots of threads you call it wait and signal. This is semaphores. The atomic can make it safe. It's correct. Always correct. So wait and signal. Inside the implementation, wait and signal is atomic. It means atomic. Okay. Here is integer. Wait and signal and acquire and release some kinds called P and V. It's same thing. It's always has different name. Always like confusing. There's some in Python like use acquire and release. Acquire and release. And in some textbook use P and V. Wait, remember it's the same thing, different names. The wait means counter decreased by 1. Signal means counter increased by 1. Increased by 1. So wait here if S is 0, it means no resource. So wait, if S is 0, it means no resource. It will sleep. This thread will sleep. If the S is greater than 0, though, that's here await. Await, that means it must be wait, the S is greater than 0. That means we have a resource that can decrease by 1 allocate resource to this thread. So this await. This await means if equal to 0, go to sleep. Here is the signal is finish the work. The resource, recycle resource is increased by 1. Okay, this must be atomic. We can implement by some atomic instructions here. And await here must be implemented by some waiting queue. So if it's wait doing context switch and put into the waiting queue, and then signal here we must wake it up. That's the implementation. Okay, now we can say semaphores. So counting semaphores, we have an integer to counting the semaphore. So binary semaphore can simply implement the mutex lock. We can use the binary semaphores. The lock is a resource, only have a 0 or 1, right? 0 or 1. We can use a binary semaphore to implement that. Semaphore can also solve various synchronization problems. Use that lock, like we said, use that lock and solve some many other problems, like at the beginning we discussed the bounded buffer, producer and consumer, and control the access of a given resource. Finite number of instances. For the number, the semaphore number can use to counting the number of resource. Okay. Oh yeah, here is also in the today's quiz. Consider two concurrent running of a process P1 and P2 that require S1, P1 and P2 that require S1 happen before S2. So P1 is a one process, P2 is another process. P1 has a S1, P2 has a S2. S1 is a critical section, S1. S2 is also a critical section. That's we want S1 happen before S2. That means S2 happen after S1. How can we implement? Use the semaphore. Use semaphore. Okay. How many semaphore you want to use? Okay, good. I know the first time learn that it's a little confusing, right? We need one semaphore, like a semaphore. We initialize it to 0. Okay, give you an example. Here, 0. Like we want what do we want? S1 happen before S2, right? F1 happen before S2. So yeah, S1. This is the P1. Remember, P1 and P2 are running at the same time. Keep in mind, P1 and P2 are running at the same time. Yeah. P1 run S1, but P2 here is wait operation for semaphore. This is initial to 0, because wait means here 0, no resource. P2 is waiting because the semaphore here is 0, no resource. Then P1 after running to here, signal. Signal means release a resource will increase the semaphore counter by 1. Here, semaphore, this is 1. And P2, I find out, this is become 1. We have to resolve. So here, P2 will wait operations. We can do in the wait operations and decrease by 1 and can run P2. Right? So this can implement S1 happened before S2. Remember the quiz question? It's not a 2, it's a 3. I can give you S1, S2, S3. P1, P2, P3 must happen in sequence. Good. Okay, this is feels good. Yeah.
So we can have multiple semaphores, so let's say.
Yes, we
If
can.
you have 10 processes, you will need, let's say, 9 synchronization things, one of them.
Usually there's a theoretical minimum using of semaphore, but we never. But at our level, we don't care about how many semaphores you use. There's a minimum number of semaphores they use. Yeah. Because some semaphore you don't use here, you can use in other ways. First, be sure your answer is correct. Then think about how to use a semaphore here. Is that correct? Okay, correct. How about the 3 S1 P1 P2 P3? If here is P3 in the quiz, so P3 there. S3 want to happen after S2, so S2 here must signal the other semaphore, right? The other semaphore, same way. Here, signal another semaphore. P3 get the semaphore. Okay, got it? Okay, semaphore. So counting semaphore can be used to control the access to a given resource. Given resource. The semaphore is initialized to the number of resource available. Initialized to 0 because only have one resource. And initialized to 10 because you have 10 resources. 10 resources. And each processor wish to use the resource. Want to use the resource, use the weight. Use weight the resource. Until the semaphore is greater than 0, means we have the resource. And after using the resource, once you release the resource, it perform a signal. So give back the resource and use it. Wait and signal. It must be impaired. Oh no, not always be impaired. But keep in mind when you use the resource must be signal, like signal. Give back the resource. When the count of the semaphore goes to 0, all resources are being used. So then it will block. Then all the other process will block until it be greater than 0. Block is here is avoid the busy waiting. Right? We use the semaphore to try to avoid the busy waiting because our work is very heavy. It's much longer than context switch, very heavy. So we use a block. This block means doing context switch, sleep, and then when the context is greater than 0, oh, we have resource, we can wake up the process. Good. So that's why I always say use semaphore since no busy waiting. No busy waiting. Okay. So here is here is discuss how can we implement so each of the if we implement this use some atomic instructions that has a busy waiting problem. Avoid busy waiting, we need to maintain a list of processes that are blocked and waiting for it. We need a list of processes, right? To maintain the list of processes that waiting or blocked. When the semaphore become available, one of the process can be work up and scheduled to execute on the CPA. Not the list of process, the list of process. Okay, waiting as a so each of semaphore that is associated with the waiting queue. Yeah, all this is to avoid the busy waiting. Remember, and each semaphore have two data items, the value and the pointer to the list of the value as an integer. Value is an integer, and that is a pointer to the list of processors waiting. So how many to the waiting? If the value is 0, all of the wait. If the value is greater than 0, then it can wake up one block process. And then wait and signal must be atomic, right? Atomic. Two additional operations like block and wake up. Need to block, put into sleep, wake up. Okay, wake up and put into the CPU running queue, the CPU ready queue. This is the data structure, so values and list to the waiting queue. This is the implementation. This is implementation to avoid the busy waiting. Okay, so semaphore you can implement in a busy waiting version, but we want to use semaphore to try to avoid the busy waiting. Use this implementation. Okay, good. And all our current language like C or Python is this kind of version. They don't have a busy waiting. They don't have busy waiting. Okay, this is a semaphore no busy waiting implementation. Okay, block. So wait as a value is decreased by 1, and if decreased by 1, so this value can be less than 0. If less than 0, still can go in here. So if the S is less than 0, it's blocked. It's blocked to the waiting list. Blocked. And signal operations, you can if the value is increased by 1. If the value is less than 0, remove the and put into the and wake it up. So block and wake up. Block and wake up to avoid the busy waiting. Good. So remember this implementation, the semaphore values may be negative, but doesn't matter. If a semaphore's value is negative, it means that the number of process waiting on the semaphores, Right? The implementation of semaphore using waiting queue may result in deadlock and starvations. Deadlock is nobody can move. Starvation is some cores always free, don't have work to do. Starve. Okay. Deadlock starvations. Let's say is this what's the problem with this? What's the problem with this? Let's S and Q are two semaphore initialized to 1. Is this correct? What happened? Okay. Yeah, try.
Well, they would be signal the way.
Correct. That is bad. Because they're waiting for each other. Here's waiting for S. S will be waiting S. Okay, it's good because S and Q each 1. Waiting for Q is good. But now waiting Q is blocked. It's blocked. Right? It's blocked. And waiting for S here is also blocked. So P0 and P1 never from us to here. That will come here. Right? This is deadlock counts. This is the misusing of semaphore from the deadlock counts. Deadlock counts. That's why I say semaphore sometimes are hard to use. And starvation means a process may never be removed from a semaphore queue in which it is suspended. It's always in the waiting queue. And have no chance to examine. That means the starvation. Starvation stuff. Okay, let's see a code of see a code. Semaphore deadlock. Yeah, this is I use S1 and S2. Right, S1 and S2. Yeah, first is okay. This is I use semaphore like this code is I use that's what's this code? S1 running first line, S2 running after S1. I use the semaphore to control that. You see the output is S2 waiting for S1 and S1 down, signal S2 running after S1. Say here the semaphore, the S1 release the semaphore here, and S2 acquire a semaphore, S2 can run. So in S1 release semaphore, S2 acquire semaphore, it can run. Okay, the deadlock happens here. Deadlock happens same as before. So S acquire, P0 is S acquire, and Q acquire. P1 is Q acquire and S acquire. S acquire semaphore. Acquire is acquire. Oh, here acquire release in the Python. Acquire release Python. For example, is signal, wait and signal. Okay, the different names. You say here is I run it. Let's see what happened. Because I must run it. So P0 and P1 got stop and wait. And what happened? So how Python can deal with it? Deadlock. It's a deadlock happens. P1 wait until with it's a deadlock. So see, they all can not going past the. They can acquire S and it cannot acquire Q because Q is acquired here. So it's a deadlock happens, right? How Python can deal with that? Who knows? How Python can deal with that? This is important. Okay, who knows? Deadlock happens. How do we know that's a deadlock? If I don't have this printed out information, how do I know it's a deadlock? Think about it. Yeah, any idea?
You wouldn't know.
Correct, you never know that. The program will stop here. Will stop here. It don't run. And it never give you some warning, error, nothing. You see, it's stopped here. It's still running. Deadlock, not terminate. It will not give you any information of deadlock. And debugging is well, debugging that you side is locked there. It's locked with acquired time. So never show you any hey. So that's the Python. This is the C, this is Java. All I know is this screen up with all totally the same. When there's a deadlock, it just stop. Nothing happened. Okay, it's hard to debug this kind of code. Deadlock happens. Nothing tell you. Okay, so this I must restart the code, restart the kernel. Okay, make it stop. Otherwise, I cannot make it stop. Okay, get it? This is the Python. The Python, Java, C++ don't have a good mechanism to handle with the deadlock. They just stop there, doing nothing. That's why we must have the Golang. Golang has in Golang, the deadlock is a exception. When deadlock happens, the Golang will throw out the exception. Oh, deadlock happens. Okay, later we'll show the code of when we go into Golang, we'll show the code. Okay. Okay. Okay, we have two left. Two left, then we're done. Oh, there's a semaphore in C. In C, we still C still supports semaphores. It includes head files. It's a semaphores. And the name is changed. It's become a wait and post. So always have different names, wait and post. Wait and post. When you use it, totally the same as the Python's acquire and release. Different names. Okay. Okay, different names. This is semaphore init. Semaphore init. You need to pointer to this is a structure, the flag. Acquire the semaphore and release the semaphores. Okay, return here. Oh, here return to 0 semaphore created with no errors. No errors. Otherwise, return non-zero values. If it return non-zero values, it always gives you some error. It's the errors. So this is a systems. Return 0 means correct. Return non-zero means error happens. This is the semaphore the integer value initialize to n. Okay. So first is the pointer to semaphore. Second is flag. Third one is the semaphore's initial values. In C, it's a little complicated. Python is very simple to use. Okay. That's for today's class. Now you have enough time to finish your quiz. Good. Any questions for the quiz?
Yeah, what's the new forward?
Yes, 4 o'clock.
Or was it real time?
Oh, expand. Yeah, at least a certain word. So not constitute that the expand part. Without explanation, you can do it. Yeah. And now it's people, Who has a paper writing? You can give me. And this I think it's very outstanding. Yeah. All question one question, you must give explanation, at least 30 words. If you simply answer true or false, yes or no, you will not have smart. Right? Right, son? Yes, definitely. I think that's really good. I understand. You finished? No, yeah. Sorry, I'm valid. That was thinking of my for you can doing some construct, you did what you did what big policy. And it's different. Yeah, same policy, different policy. It's not really usual, I think what's the issue? It wasn't an issue, like. Yeah, issue actually. Good.